morning, I'm João from Brazil and I'm going to present problem number 6, the Woodpecker Toy. The problem consists in investigate and explain a motion of a woodpecker toy. First of all, I'd like to show you the woodpecker. That's the woodpecker toy, and we will investigate this movement. It's only a demonstration. I'd like to give to the jury to analyze, to see if they want. As you can see and wait. So first, here are our contents. First, our introduction. We're going to analyze the woodpecker theoretically. Then we're going to make experiments and compare the theory with the experiment. And then make a conclusion. First of all, we can see that we have two different stages of movement. The first stage is a fast stage, is the beginning of the movement, and we have a non-constant angular velocity. And in the second stage, the total energy in the system is constant, and the angular velocity is constant too. The second stage is the main stage that we will analyze, because it's the bigger and where the most of the effects happen. In the oscillation, we have two different periods. First, when the woodpecker is stopped, and then when he's falling. When he's stopped, we have the elastic force plus the weight force is equal to the friction. But as we have oscillatory motion caused by the spring, the sleeve loses contact with the rod, and the woodpecker starts falling. And again, when he contacts again, the force equalizes again, and we have the woodpecker at rest, as you can see in these pictures. For the fall of the woodpecker, we neglect the friction, only the fall of the woodpecker, because it's a really small fall. And considering this free fall, we have the equation for this delta H. And considering this average angular velocity, we can, using these two equations, and comparing this angle with the angle of the rod, we can get to this equation where B is the sleeve's internal diameter, R is the rod's diameter, and A is the sleeve's height. And as we will see later, we will analyze all these parameters to see if it's valid. Initial conditions are neglected as the dimension of the sleeve is what controls the amplitude. These initial conditions are only important for our first stage, as we will see later. And for the second stage, we won't have the importance of this initial condition. And as you can see, the period is independent of the amplitude. And V is the reduced mass, analyzing the mass of the woodpecker and the sleeve's mass. Here, to analyze the angular velocity, we compare analyzing the woodpecker when he's at rest. We have that the potential energy of these small falls plus the less energy is equal to the kinetic energy transferred to the woodpecker to his oscillatory behavior. And analyzing this, we can get this angular velocity. Here we have theoretical graphs, and as we can see, the angular velocity and the angle of the oscillation is constant, and we have this instantaneous decay, the velocity due to this collision with the rod. Here we have a simulation of the woodpecker, and in this simulation is the position of the center of mass of the woodpecker. In this simulation, we can clearly see this is the first stage when you don't have a constant angular velocity. And after a small period of time, we have this constant velocity. And the rate of fall is always constant for all the second stage. Here we can see the torques in the systems that make the woodpeckers oscillate and stop or falls. And we have the relations between the parameters and the torques. As we analyzed later before, B is the internal diameter of the sleeve, A is the sleeve's height, x0 is the initial length of the spring, elastic force and weight force of the sleeves and the woodpecker. And to also the torque from the normal force And to this we analyze the torque front friction force that makes the woodpecker stops, that we see that he stops. The rod inclination, we can also get a limit for the inclination of the toy. There is a maximum angle where the woodpecker works. And analyzing this, the elastic force plus the friction, we can get that's just like a simple inclined plane, that where tangent of theta is equal to the friction coefficient of the woodpecker. And we will see this later on our experiments too. The beak and the lateral oscillations are parameters that are not really important for all the movement. The beak decreases the amplitude of oscillation, and as you can see, not the period. And the lateral oscillations that happen in the toy are only due to the rod oscillations. So we can fix this and make, and this won't interfere in our experiments, in other measurements. Here, using a high-speed camera of 4,000 FPS, frames per second, we can analyze the movement of the woodpecker. As you can clearly see, we have these two moments when he's stopped, and this fall when the mass is going down, all the system is going down too. When the mass is going up, the system is stopped due to the inertia of the system. And after analyzing this video too, we can get other experimental results. But you can clearly see these two phases, these two periods, and the constant falls of the woodpecker. These are our materials. To measure the position of the woodpecker, we could use photo gates that are really we have a precision, a really high precision, and other materials. We develop different woodpeckers to measure, to make our variations of height, internal diameter, and mass of the woodpecker, to analyze all the important parameters. Here are our experiments. We analyze first the lateral oscillations to see that they won't influence in other experiments, and we will talk better about each experiment when we get to them. First, we can see fixing a movement of the rod when it is not fixed, and a movement of when the woodpecker on the rod is fixed. We can clearly see that these oscillations are only due to the rod oscillation. To analyze the velocity, as I mentioned before, we used photo gates and the variations of the woodpecker to analyze each parameter that we mentioned before. First, we have this graph comparing our theoretical graph that we have that these small falls happens on each period of oscillation. So as we have all the parameters, we can create this theoretical graph, and using the photo gates and our setup, we can calculate the experimental points. And as we can see, they fit really well, and we have a linear variation and a constant rate of fall. But this is for a specific limit, or when we have all the fall. Analyzing these oscillations, this period of oscillations, we have another graph, and using this high-speed camera from 4,000 FPS and the Woodpecker Toy, we can get this graph. Is exactly the same as in our simulation, and we have small errors due to the rods and sleeves imperfections, but we can clearly see that we have constant oscillation and we have a constant angular velocity, and agrees with the simulation we showed to you before. Analyzing the leaves height, we have that increasing the leaves height, you have this delta H is bigger, shown in our equation, and we have the velocity of fall increases. The leaves internal diameter, as we could see, is the same as in the, the same of the height. Delta H is bigger and the velocity of fall increases. The mass, you have a different situation for this, that increases the mass, the way torque increases, So the angular velocity increases and the velocity of fall decreases, as we can see in this graph. The spring's length that changes the torque of the systems. We have that increasing the spring's length, we increase the angular velocity, and the velocity of fall decreases. And in that equation, we show that the inversion proportionally to the velocity of fall inversely proportional to the angular velocity. With the inclination, we analyze these, and we got a limit angle for the phenomenon, the movement. And we have this inflection point, and we have the friction coefficient between 0.83 and 1 for the friction between the rod and the sleeve. And with analyzing the friction, we have a time with oil that decreases the friction, and normal without oil. And we can clearly see that the time of fall decreases. That means that the velocity increases. As you could see, we have this decreasing the friction. We have this bigger time of this oscillation, and this oscillation decreases, and the velocity of fall increases. So in conclusion, the lateral oscillations are indeed caused by the rod oscillations, as we see in experiment 1. The woodpecker presents a constant rate of fall during the movement, as we can prove in our experiment. Woodpecker presents an harmonic oscillation, as you could see in our experiment 2. Oscillation during the fall are defined by the sleeves dimension, average velocity decrease with the increase of mass, or of the spring length. And there's a maximum inclination for the effect to happen. So that's it. We hope that we present all the points and all the parameters. And the greater the friction too influence. And these are our references. And thank you for your attention.
Well, as you mentioned at the beginning, when the woodpecker was resting, can you see the graph?
When what?
When the woodpecker was resting, I think it's second or first graph.
It's
second,
third.
No, third. The beginning.
No, the second.
Yeah, this one. Yes, this is the first one. Is in this position the woodpecker resting?
He stopped, as we could see in that high-speed camera, the video from high-speed camera. He
Stopped
stopped
that
for a
position.
moment, and then continues falling, and stopped for a moment and fall again.
Okay, I understand that. Do you say even how the system started? How
Yes,
do
we
you start?
give
What do you add?
initial amplitude to the initial deflection for the spring.
Yes, so you increase actually the which energy?
The elastic energy for the
Elastic
woodpecker.
energy. Okay, but the elastic energy for spring, I think it only works in right spring here.
Opponents, this is the time for clarifying question. The discussion comes later.
Okay.
So if you have things you want to clarify, you only have 40 seconds left.
Okay, and I see that you said the mass decreases the mass. It also decreases the falling velocity.
Yes,
Is this decrease the average falling velocity or the falling velocity of actually one phase?
yes, no. We analyze, as I said, the second stage is a small period of the oscillation. Analyzing the second stage, you have this decreasing of the velocity.
Okay.
Alright,
I
you now have
will
3
be
minutes.
talking about this. You analyze in this.
Yes, precision of spring, I think.
Yes, but
analysis
we can
is-
consider in this. Let me talk. We can consider the spring as a torsion spring, and we can apply these equations for this deflection of the spring in the vertical, not in the horizontal. We can apply these equations considering.
You have on your woodpecker, I see you have spring like this, right?
Yes, but we can analyze this when he acts, has a behavior of this kind. We can apply this for these equations for this. They are applicable too, and we can put.
Okay, now you said somewhere in your presentation that there is a constant angular velocity. I think it was on slide number 10. Yes, here, well, this is the angular velocity, the left graph, yes?
Yes, this is the angular velocity.
Well,
It's a theoretical graph. as I showed.
Okay, but you said somewhere before in your presentation that the angular velocity is constant.
Yeah, no, the rate of this angular velocity is constant. You have these oscillations are always constant. You have the same oscillation for the same period.
Okay, I understand that. But
The same.
this is not a constant. Really.
Yes, you have similar. You have the same
Yes.
oscillation for the same time.
Okay.
That's what I mean.
You say that the peak is big important for the case.
Yes,
Or
change.
even without a peak and we interfacing with the
He changes only the amplitude of the movement.
yes, but amplitude also affects on
Yes, the
time.
amplitude. We change this. The period is constant.
Okay.
And as I showed, this amplitude, this initial amplitude is only important for the first stage. Then we have this,
Okay.
the first when it
you
falls
said you
is
showed
with this concentration.
You showed a two videos on which
Sorry?
you showed two videos of fixed rod, of fixed rod.
Yes, yes.
Can I see again those two videos?
Yeah. And when I say the rod oscillate, can I pick the woodpecker for a moment to show? When I'm talking about the lateral oscillations, I don't talk about these oscillations of the woodpecker. I'm talking about these oscillations of the woodpecker. Because when the rod is not fixed, the woodpecker oscillates in this.
Okay, but can I see the video? Which rod should be fixed? The right one, right?
Yes.
Can we see the video again? Is this a fixed rod or?
Because you have a small movement of the camera.
Oh, you move camera.
No. Because we move it. This move we make with the hand. Okay, that we should have fixed the camera. Okay, I'm sorry.
Okay, I think
That's a good point that we could increase this.
Okay.
Improve this.
You said that woodpecker maximum angle for working is 54 degrees.
Yes, for a woodpecker, we analyze that we have the main important parameter in this case is analyze that we have an inflection point.
Yes.
Yes, because we have, as I don't know if you could see, for any woodpecker we have a maximum maximum angle to the effect to happen. And we show in this graph, the most important of this graph is analyze this inflection point. This we could give, and using the equation we could give a friction coefficient. And the most important is analyze that for over this angle we have the effect happening.
Okay. You said somewhere that when woodpecker is falling only affects the force of gravity, so G. And you said that when woodpecker is falling, I think you said that on his falling effects is only the gravity
No,
and the friction.
when he's falling.
Yes.
No, we consider first we consider we make two different analyses. Then we compare both, and we use both to get to the equation of this fall. As we have a small fall, we can neglect the friction in this period and consider a free fall. And using the equation for free fall for the time,
Okay.
that's the period of the oscillation. We can compare with the angular velocity equation, the average angular velocity, and comparing both, we can get to the equation of delta H.
Okay, but when it's falling, when woodpecker is falling, it's only falling because of the equation for free fall.
No, the equation for free fall and the equation for the oscillation.
If you neglect the friction and the oscillation, so
No, I haven't neglected the oscillation. We considered. So we considered these two cases. We made the two analyses. This analysis plus the analysis of the oscillation. We don't use them separated. We use both to get to our equation.
okay.
And the friction, as you can see, the point is in the contact between the sleeve and the height.
Okay.
That makes the woodpecker stop.
Okay, but when woodpecker is resting like now, if you put them, is there any angle? If you say that there is an angle, which is angle between the sleeve and the bow, which is maximum, and the system is started because of this, when this angle is decreasing?
That's, as I showed, given this inclination, the woodpecker will lose contact. And this, you have a fall. In this case, we lose contact, this is between the horizon. He falls, and with this small amplitude, the oscillation starts. And then he starts in a constant rate of fall for each determined dimensions of the sleeve or the mass.
Okay.
And you said about the velocity of fall, we have the average velocity of fall. And increasing or decreasing these, we can consider that we decrease or increase this velocity of oscillation. So we could analyze this.
I mean you said that the woodpecker is falling just because of gravity and not even the oscillation. I just mean that.
Okay.
Can I see the equations? These equations where the maximum angle is.
No, the equation for the fall.
For the maximum angle when it's still working.
No, we don't have the equation for the maximum.
I think you have the equations for the angle.
No, what?
For the this.
Oh, here.
Oops. Yes, yeah. Can you explain how you get to the position?
Yes, you have the friction, and we have the friction force, that is the weight plus the component of the weight, and the friction coefficient, the normal plus the multiplied by the angle, the components of normal. And then we have the equation, we have the Newton's equation, that we have the component of the weight plus the component of elastic force plus minus the friction. We have mass multiplied by acceleration. And comparing, you develop solving these equations, we have these equations here. And in the equilibrium, the angular velocity is equal to 0. And in this way, we have this equation. Okay.
So do you calculate those angle connections? I don't know. The angle between the sleeve and the angle between the bow and the angle between the sleeve.
Yes, as we could see in this video, we have the first stage.
This angle here.
Yes, using basic trigonometry.
Okay, how was the this angle in your example?
Is this angle here. Here is based on this angle. That is in function of our parameters.
Okay. So
Using trigonometry to get these to these.
yes, okay. So you use arc-stand function. What this is actually?
Yes. To get to the angle of the woodpecker, you have the scene of the angle, and use arc-stand to discover the angle. To make it clear, I don't know if you understand, this fall is only in this small fall between these 2 points of contact. Okay, this free fall we consider. Okay. Okay.
Thank you, Nicholas. Thank you for your answers.
Right? Thomas, you do have.
Basically, we have lost the friction in the contact with the rod. But we didn't. It depends on the woodpecker, because in many times it only touched his stoppage.
Okay, also I'd like to ask you, so could you please show me this video with your oscillations in slow motion?
The slow motion?
Yes. Yeah, you have the sound.
Yeah.
Yes. Yes. So, if you will look attentively, here you have some step where your toy is still moving, but it's already begin to move in this state. So, don't you think so that in this case we also have sliding motion when our toy is still moving, but
no, but in this case, when it's falling, the leaves hadn't contacted the rod yet.
So I mean that. So 2 steps like first of all you have when your toy is flying like this, then it goes like this. It already touches this point and it's still flying, so it goes some distance, and the third point when it's already
yes, I understood. Okay. First, you could clearly see that are really small. If there is a really small, and we can clearly see it. We can clearly see
as
it.
you said, this is
So it's a first approximation that we could agree. Our theory could agree.
okay. Also,
Our
I'd like
experiments could
to
agree with that.
ask some questions. So when you are proving that your oscillations are harmonic, what do you mean? How do you prove it?
We could see with the. We could see with the analysis of the video of 4000 FPS, and we have that constant period of oscillation.
And it doesn't mean that they're harmonic, because harmonic oscillations means that our oscillations can our acceleration depends on coordinates. You didn't prove it, I think.
Yes.
So also, can you open it, please? You asked some questions about
this we could see is the second stage.
You asked some question about the quantitative explanation of our motion. So some kind of. So you asked for which reasons our toy is moving. So could you please answer this question?
Which is implies movement.
So for which reasons? So
Well, the toy is moving because of the gravity and of course of the angular velocity of the woodpecker, not of the speed, which the angular velocity of woodpecker is caused by the elastic
yes,
energy.
understood. Thank you. Now I just probably have some time for preparation.
Yes, 2 minutes for preparation.
First of all, I'd like the collaboration of both teams. I'd like to emphasize that this free fall is only between the points of contact. It's not, and the friction is neglected on this fall. And the friction is really important, as I showed, that it makes the woodpecker stop and cause the oscillation. We know, as we've shown, that the velocity is variable, it's not the same. But to analyze the parameters, we calculate average velocity and analyze its variation. We can, as he told, the elastic force is not on is not longitudinal, but latitudinal. And we have the harmonic movement. We can clearly see that the period is constant. And with the video, we could consider the sliding because it's too small for a first approximation. So we don't have this loss of energy. And in this way, we could consider validate we could use our equations to compare them with the theory and the experiment. And that's it. The errors he mentioned, the graphs have errors. Probably some like these we have small errors due to the precision of the photo gate. And as you can see, we can see the errors here in the other graphs. So that's it. We hope I've made a good presentation. Thank you for the attention of all, and that's it.
Slide number 7, please.
Okay.
I presume that arc stem is the same as arc sine.
Yes.
Okay.
It's a mistake of digitation.
Okay. But so it's an angle.
Yes.
So why does it have dimensions of length squared?
Sorry?
Why does it have dimensions of length squared?
The G, you have the G, the gravitational, and the angular velocity.
No, inside. Inside is the dimension of distance. Inside the.
Please.
Then
Yes.
We use it radians. Do not.
Okay, can I ask a question? This is a question for the opponent and the reviewer. During science, you raised the point of whether it was or wasn't a harmonic oscillation. This one, a yes or no answer. Do you think it's reasonable to assume that it is a harmonic?
Actually,
A yes or no?
no.
Do you think it's reasonable to assume that it's
I
harmonic?
didn't.
Do you think it's reasonable to assume that it's a simple harmonic oscillation?
No.
No. Thank you.
Can I have another go? Your videos are excellent, but don't they actually show you that there are actually 4 phases to this motion?
For phase,
4 phases to this motion.
we separate 2 different states.
Yeah.
The first stage, the second stage, and in the second stage we analyze different periods of the movement. We don't consider 4 stages, but 2 stages and different periods in a stage.
But do you agree with me that when it's actually, the slipping motion occurs when the ring is basically in a vertical position?
Yes, but
And that happens twice with each oscillation.
yes, but it's too small in comparison of the.
I saw it. If you look at the video, you can see that the ring slips twice with each period.
Yeah, but analyzing this video, we put in a graph, and you could see that there is no. This is sliding because you can confuse because due to the
It slips.
bright of.
Slips.
No, it's
Wait,
not
wait.
sliding.
It slips again. There. It slips again. It slips twice.
Yeah, that's the moment of the fall. The slide is when it's in contact, but in this fall we can clearly see here because of the video, the brightness of the video. But after the contact that we have this sliding, and when we contact, put in a graph, we can see that this slide is considerable.
All right.
Okay.
Do we have more questions? Go ahead.
Okay, can you please go to slide 21? What is the scale on that vertical axis? Is it? It looks like it's. So is that 10,000 millimeters in the air?
The KO of conversion of the program to analyze the video. And I'd like to emphasize that we have this harmonic oscillation during each point of contact, as you can see. We have this period of oscillation during each contact.
Is it 10,000 millimeters in the air? Is it? Should that be 10,000 millimeters?
No, we have 10. 10 millimeters. Yes, it's the scale of the pixel of the video.
Okay, thank you.
Any more questions?